Hey everyone, Azim here. We are in the chapter 6 notes, the cartilage and osseous tissue notes. We're starting on, not on this one. We're starting on slide 11. We've already gone through slides 1 through 10, where we talked about the basics of the skeletal system and talked about the different types of cartilage. We're starting here on slide 11. We're talking about osseous tissue. Fancy word for saying bone tissue. This prefix os, os, os means bone in Latin. So osseous tissue is bone tissue. So what is bone tissue? You probably know all about the calcium that we find in our bones, and that is true. We find a ton of calcium. About 66% of the extracellular matrix of bone is calcium phosphate. Don't worry about being able to draw this or anything, but pictured right here is a molecular model of the calcium and the phosphate, PO43-, linked together in a matrix, a nice lattice framework. And when you link together these molecules, these ions and atoms in a very particular arrangement, it becomes very strong. So strong that you can resist a lot of tension. Calcium phosphate, the mineral component of our bone, the non-living part of our bone, is very strong. Collagen, I suppose, is not living either, but collagen comes from living things. It comes from our cells. Collagen fibers, the protein in our bone, in the extracellular matrix, makes up about 33% of our bone. The living part of our bone, the cells, make up 2% or less of our bone. So our bone is living, but it's very small pockets here and there. So we're going to see where the bone cells live, osteoblasts and osteocytes. The way that bone is arranged, depending on the type of bone, but overall bone is arranged such that there's very dense bone towards the outer portion. That's compact bone. And then towards the inner portion of the bone, towards the middle, it's very branchy. It has a lot of these bony networked branches. That's known as spongy bone. There's compact bone, it's compact, and then there's spongy bone, and it looks spongy. It's got space in between it. We're going to take a look at how calcium phosphate, shown here, a model of it at least, combined with collagen fibers, this shown here, can come together to make the extracellular matrix of bone strong yet flexible. I know you don't think of bones as flexible, but they are a little bit. Otherwise, any impact on your bone would just instantly shatter your bone. Some things can shatter your bone, but most things that you hopefully encounter in your daily life won't shatter your bone. Let's talk about compact bone first. Compact bone is dense, it's solid, it forms the walls of bones. Just like the walls of our houses where we live are nice and solid, we want the walls of our bones to be nice and solid. It's protected. It's the thing experiencing the most contact when you're interacting with the world. And also providing a framework for when you put stress on your body, for jumping, for punching, for pushing, for lifting. You're putting stress on your bones. You want to put stress on your muscles, but there is stress on your bones. And you want the walls of those bones to be strong. Compact bone allows for that. To allow for that, we have something called osteons. I'm going to switch back and forth between complete anatomy to show you what an osteon is, but an osteon is a column shape. It's a column shape arrangement of bone. It goes up and down the length of a bone. An osteon is a unit that repeats over and over again, and it goes up and down the length of a bone. Let me show you this in complete anatomy. If you go to the hub and click on models, and then bottom left, click on models, and then click on detailed. See the tab that says detailed? Click on detailed. I'm going to click on bone cross section. Here's our bone cross-section. So this is just a sliver of a bone that's been cut in cross-section, transverse cut. So you can see the outside of the bone. That's what we're looking at here. If we look at the face that we cut, you'll notice all of these little circles here. Here, here, these circular arrangements. Each of those things that I've circled, those are osteons. If we go closer, they've isolated one osteon for us. Here is an osteon. Here's another one. Here's another one. In cross-section, they look circular. When you longitudinally cut the bone, it looks like a rectangle, like a column. So an osteon, it's just a bunch of columns smushed together, going up and down. And if you know anything about columns, columns are very supportive. They hold up buildings. These columns hold up the walls of your bone. Again, here it is in cross-section. A single osteon would be this whole thing in cross-section. An osteon in longitudinal section would be this, all of that. We'll come back to this. And I said that the compact bone is only found on the outer walls. So compact bone is this. This is all compact bone going around the whole thing. The spongy bone, do you see the bone here and here and here? It's branching. This is all spongy. Spongy bone is found towards the middle. Often there's some, well, not often, but depending on the type of bone, there might be something completely different in the middle. We'll get to yellow marrow coming up. So, osteons. We see a slice of an osteon shown right here. This is the slice of an osteon. Within an osteon, you find many components. A single layer, a circular layer, is called a lamella, plural lamellae. A lamella is composed of matrix, extracellular matrix, the calcium phosphate and collagen. So in a given lamella, again, this is just a sliver, so this should go all the way around. In a given lamella, you have extracellular matrix. There's one layer. And then in another lamella, it's a smaller one because it's towards the middle. We have another layer, and then another layer, and then another layer. There's a lot of layers. How many? It depends. If we look at it in the actual histology, what I'm circling, let me start that again. A single osteon would be this in cross-section. And then a single lamella would be roughly this amount. That's a lamella. Lamellae are layers that go in circles. These circular structures provide a lot of strength, and they go vertically to provide that longitudinal strength. The center of an osteon is dark, stains dark in this particular stain. The center is called a central canal. You might hear it called a Haversian canal. I'm going to call it a central canal. It's in the center. The central canal, it looks like a circle here. If we saw it in a longitudinal section, it would be long. You have blood vessels and nerves running up and down the bone. Our bone, unlike cartilage, our bone is highly vascular. Here's evidence of that. One structure that allows for blood vessels to run through bone. Blood vessels are allowed to run up and down bone because of central canals and nerves, which is why if you've ever broken a bone, you'd know it's painful. We need those blood vessels to branch. So we have larger blood vessels going up and down the bone, but we need to get deeper into the bone. But bone is very solid. The extracellular matrix is going to get in the way of the blood vessels. To bypass that, literally, we have tiny little passageways, tiny small passageways within the extracellular matrix. Those tiny little passageways, which I'm coloring in at the top here, those tiny little passageways that you see as little tiny dark lines here in our histology, those are called canaliculi. Canaliculi, tiny canals. A canaliculus, singular, canaliculi, plural. These are passageways in the extracellular matrix that allow blood vessels to pass from the central canal to the cells. Where are the cells? The cells are within lacunae. Lacunae appear as these dark spots. The lacunae here and osteocytes don't appear like they do with chondrocytes within lacunae, where you see the nice space. The space here is very tight, so you'll have to trust me once again that there is a cell inside of the space. This image up here shows an osteocyte inside of a lacuna. Osteocyte inside of a lacuna. Osteocyte inside of a lacuna. So there are lacunae and there are osteocytes within them. Osteocytes are within lacunae. They help maintain that extracellular matrix, just like chondrocytes help maintain the cartilage extracellular matrix. They weren't always osteocytes. If this is an osteocyte, if this is an osteoblast is the precursor. It's building. Osteoblasts build extracellular matrix. If they're building matrix around and around and around, eventually they'll completely close themselves up. That's when an osteoblast becomes an osteocyte. Just like what we saw with cartilage. Central canals allow blood to go longitudinally. Canaliculi allow it to go within a single osteon, allow it to go horizontally in the cross section. But what if we want to go from one osteon to the next? Canaliculi are just within a single osteon. If we want to go from one osteon to the next, it's not actually shown here, but we can connect this way. That would be called a perforating canal. Perforating canals go horizontally, a bit more visible in the cross section, if it's cut perfectly. In this picture, it's not shown. Let me go back to complete anatomy to show you that, and then I'll show you some histology. Maybe just the complete anatomy. Let's see if it's sufficient. One second. Here we go. Okay. So again, here's our model of bone. In longitudinal section, you can see the central canals going up and down. And then going horizontally this way here, connecting osteons. These are perforating canals. Perforating canals go horizontally, central canals go longitudinally. In this part, what they've done is parse out the different lamellae Here's one lamella, another lamella, another lamella, another lamella. Really what it looks like is this all together in a single osteon, but that's showing the different layers. If you go to the histology videos, take a look at the compact bone histology. This is 40x. We're just seeing a sliver of bone. This has been stained so that you can see all the features. Here is 100x. You can see how here's one osteon. You see the central canal here. So that central canal is just nice and round. But do you see how this central canal kind of lengthens? That's a good sign that there's a perforating canal that's going to connect from one osteon to another. Here's an osteon, 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 osteon. Look for the central canals to know where the osteons are. We'll of course go over this more in lab, but let's take a look at 400x. Here at 400x, you can see the central canal, the rough outline of an osteon. You can see a given lamella. I'm just outlining one. You can see an osteocyte and a lacuna. There it is, osteocyte and a lacuna. And then those tiny little lines that you see coming out makes them look like spider legs. Those are canaliculi. Once again, we're at 400x, looking at compact bone. Hope you got that. My computer's messing up. All right. We'll, of course, look more in lab. Switching back. You can see those osteons in the sliver of bone. Here's our sliver of bone, cross-section, longitudinal section. Osteon, osteon, osteon in cross-section, osteon in longitudinal section. They're columnar, they provide longitudinal strength. Because these osteons are parallel to the bone axis, they provide strength longitudinally. They do not provide strength laterally. That means if you get hit from the side, it may not provide, I mean, it's dense, so it'll be strong, but it might not be the most strong. There's nothing, compact bone itself is not braced for a lateral hit, like a sharp lateral hit. So once again, once again, it's great for compression and tension in this lateral axis. Longitudinal, excuse me, in this longitudinal axis. It's great for longitudinal compression and tension. It is not good for so much lateral impacts. It's good for gravity, not good for lateral impacts. So what can we do to cross brace our bone? For cross bracing, we need a different type of bone, arranged completely differently. That's why we have spongy bone. Spongy bone has branches, and these branches allow for cross bracing, allow for lateral support. You might see it called trabecular bone. You might see it called cancellous bone. I'm going to call it spongy bone. The reason why it's called trabecular, the word trabecula, or plural trabeculae, those are branches. Trabeculae means branches. In the histology down here, it's the pink stuff. The pink stuff in this stain is the bone. I know it looked very different in that compact bone. It's a different stain. So here, the pink stuff that's the calcified matrix, and when we get closer, we'll see the cells. These parallel struts, these branches, provide lateral support, like I just said. And also a benefit is that it's a very open network. It reduces bone weight. If we had just a solid piece of bone, it might be really strong, but it's going to be very heavy. Imagine if we had to carry tons and tons of weight in bone. We would have to be massive, which means we'd need to eat more food for energy, and that is not good for survival when you have to waste so much energy on moving your body. So evolutionarily, it makes sense that we want to reduce the weight of our bone, and one way we do that is with spongy bone. So spongy bone plays many roles here, and we're going to see it plays even more than what I just discussed. It has an open network, and it allows for cross bracing. The space, here's more histology of spongy bone. The space in between spongy bone is not empty. It's not just air. There is stuff there. There's tissue. And we can fill it with one of two things. We fill it with either yellow marrow or red marrow. Yellow marrow is found in the middle of long bones. We'll get to the definition of a long bone coming up, but as the name suggests, it's longer than it is wide. Long bones on the inner portion, it's called the medullary cavity. Long bones have yellow marrow, and all yellow marrow is adipose. Fat cells, adipocytes. You can see that here. All of this stuff here in this histology is adipose. The word for the shaft of the bone is the diaphysis. We'll also get to that in a second, what that means. But yellow marrow is found in between spongy bone, fills the medullary cavity, the main cavity of long bones. The other type of marrow that we have that can fit in between the spaces, in between the trabeculae of spongy bone, is red marrow. Red marrow, it appears denser. There's more cells, not those big round clear cells that we see with adipocytes, but lots of darker, denser cells squished together. These cells are for making blood cells, red blood cells, erythrocytes, white blood cells, leukocytes, and platelets. We can find this at the proximal epiphysis. The epiphysis is the end of a bone. We'll get to that term again in a minute. That's where we find the most of it. It's also found pretty much in between the spongy bone of every other bone. But the highest concentration of red marrow is in between the spongy bone of flatter bones, like our skull and our ilium, and also at the ends of longer bones, like the femur and the humerus. I want to point out that in red marrow, we have these darker cells. Those cells are going to develop blood cells, but there is still adipose. There is still adipose in red marrow, but if you see all those darker dots, those darker cells, then you know we're in red marrow. In this histology, what I'm highlighting in green, that's the spongy bone. So one of these branches is a trabecula. If you look really closely, can you see that there's a dot surrounded by a white space? Dot, white space, dot, white space. These are the osteocytes. There are no osteons like what we saw with compact bone. It's not arranged like that. Instead, we have these branches of trabeculae osteocytes inside lacunae. I threw out a bunch of weird words just a minute ago. These words are referring to different parts of long bones. Long bones are the bones that we typically find in our appendages. Not every bone in your appendage, like your patella is not a long bone, but the bones of your arms and your fingers, the bones of your legs and your feet, minus your wrists, minus your ankles, not the carpals, not the tarsals, those are different. But long bones, they contain marrow within medullary cavities. The medullary cavity, the biggest one, is the center portion. The center portion, the region is known as the diaphysis. The diaphysis is where we can find that medullary cavity filled with yellow marrow, which is made of adipose. It's a storage area for fat. If you've ever eaten bone marrow from, say, a cow, then you'd know that there's some good fatty marrow in the middle. The ends of the bone, that's the metaphysis. I'm sorry, the very end of the bone, is the epiphysis. Epi means on top or to the side. So here's one epiphysis. Here's another epiphysis, what I've circled there in blue for this long bone. And at the epiphyses, in between the spongy bone, is where we find red bone marrow. There's tends to be more at the proximal end than at the distal end. And there's more spongy bone filled with red marrow at the proximal end of these bigger bones. In between the epiphysis and diaphysis is this region, which I'm circling in green. This in-between region is known as the metaphysis. The metaphysis is a narrow growth zone. As you might know, bones grow, especially when we're younger and into adulthood, and except in certain situations, in some conditions, but bones are growing. And this region, the metaphysis, is where bones are lengthening. It's known as, this is the growth zone. So epiphyses on either end, diaphysis in the middle, metaphyses in between, bordering the diaphysis. Red bone marrow is found in between the spongy bone of the epiphyses, mostly the proximal end for long bones, and then within the diaphysis you have the medullary cavity, and the medullary cavity is filled with yellow marrow, adipose. Take a look at the bottom right. Let's start down here. What we're looking at here is spongy bone. The pink stuff is the extracellular matrix, the calcium phosphate and collagen. It's already labeled here, but you can see osteocytes in their lacunae also surrounded by that matrix. So what's bordering on the edges of the spongy bone? On the edges of the spongy bone, which I'm going to color in dark blue, you see a bunch of cells here. What are these cells? Well, first, this layer where we find these cells, this layer of the spongy bone, you can see I'm highlighting in this image now. What's surrounding the trabeculae, this is known as end osteum. Endo means to the inside, os means bone. So it's the inner lining of bone, endosteum. So I'm not talking about the marrow. If you look back at our histology down here, this is the marrow space. I'm not talking about the marrow space. So this happens to be red bone marrow. You can see the darker cells there. They're not osseous. They're not adipocytes. But the endosteum is lining the trabeculae of spongy bone. And in the endosteum, we find osteoblasts. Let me color it the way I colored it here. These are osteoblasts found in the endosteum. These are the ones that are putting down new calcium phosphate and collagen, producing more calcified matrix to make more bone. You can find osteoblasts in the endosteum. There's also osteoblasts in the periosteum. The periosteum is in the outer lining of bone. You have this layer where you can find osteoblasts lining on the outer portion, the superficial to the compact bone. So you've got endosteum lining in the inner lining and also superficial to compact bone. Both layers have osteoblasts. Two places you can find osteoblasts. Now, we've talked about osteoblasts, which create bone, osteocytes, which maintain bone, and they're surrounded by lacunae. But I talked about how we need to remove bone as well. To remove bone, we need another cell type. This cell is known as an osteoclast. Osteoclasts remove bone. They dissolve bone. And they do this by secreting acid. Take a look at this histology right here on the bottom left. Osteoblasts are pretty small. They're standard size, and there's more of them. Osteoclasts, though, are very big cells. Look for ones that are 3 times or more bigger than most of the cells that you see. Osteoclasts are very big. They have multiple nuclei. That's what makes them big. When you have multiple nuclei, you have more DNA. If you have more DNA, you have more instructions for proteins. And now you can have more proteins. It'll add transport proteins to these cells on the membrane so they can secrete acid. That's at least one reason why it needs multiple nuclei. But these multinucleated cells, these osteoclasts, secrete acid and dissolve this bone. So you're eroding the bone, eroding the calcium phosphate. And that calcium phosphate is released into the bloodstream. And it can be used in other cells, in other tissues. Remember I said that muscle cells use calcium and phosphate, neurons use calcium and phosphate. Calcium and phosphate are important ions for things that you're going to discuss more in physiology, lots of signal transduction pathways. So osteoclasts you can also find in the endosteum and the periosteum to dissolve the bone as needed. And there's a complicated signaling pathway that we'll get to a little bit when we get to the endocrine system of how we can tell these osteoblasts and osteoclasts to either make bone or remove bone. Osteoblasts and clasts are both found in the endosteum and periosteum, but osteoclasts are much bigger and fewer in number. So that's what you're going to look for when you identify them. Now that we know what osteoblasts and clasts are, we can see the basics of how bones can grow. In the next video, we'll go over the nitty-gritty details. Osteoblasts add bone. Osteoclasts remove bone. They can work together, in this case, for appositional growth. Appositional, that's APP, that's to widen a bone. If we want to go from this very small infant bone to this much wider, stronger adult bone, the bone has to get bigger. We have to add bone. But we're not just adding bone, we're also removing bone. Remember my remodeling example? Not only does the bone get thicker, you can see the wall of the compact bone getting much thicker, but the medullary cavity also gets bigger. If we want the medullary cavity to get bigger, we need osteoblasts to deposit bone to the outside. Osteoblasts ossify, while osteoclasts are resorbing bone. The term resorb, or if we're talking about the action, it's resorption. It's weird, it's with a P. Whoops, resorption. If we're talking about resorption, osteoclasts remove bone from the inner lining to make the medullary cavity larger. So we're making it proportionately bigger rather than just adding a ton of bone that can weigh us down and not give us enough space for things like yellow marrow or red marrow. Appositional growth is when the bone widens. Bones also lengthen. The term for lengthened growth is interstitial growth. We've seen this word a bunch of times already now. Interstitial just means in between. Why do we call lengthening in between growth interstitial growth? The reason is because we have a region of our bones, for long bones specifically, known as an epiphyseal plate. This epiphyseal plate is made of hyaline cartilage. This epiphyseal plate is made of hyaline cartilage. At this epiphyseal plate, the cells that are closer to the medullary cavity, they die. Chondrocytes die. And instead, what's happening is that there's movement of osteoblasts coming up this way. Osteoblasts invade. They can do that by undergoing mitosis. So we're replacing cartilage with bone on that inner edge. Chondrocytes will actually continue growing on this outer edge. Oh, it says it right here. Chondrocytes divide and enlarge, so they undergo mitosis. All the while, the osteoblasts move. So we're continually lengthening the bone, and for a time, for a good amount of years in our lifespan, we have cartilage moving along, so to speak, like a wave of cartilage growth as our bone grows as well. That's known as interstitial growth. Once again, the chondrocytes bordering the calcified matrix start to die. There's a lack of nutrients, while osteoblasts invade the area, undergo mitosis, secrete more matrix. Appositional is wider, interstitial is longer. In the next video, so starting on slide 21, in the next video, we'll talk about the different types of ossification, which involve both appositional and interstitial growth. These two terms only talk about the direction of growth. When we talk about ossification, it's how it grows, the mechanism of it. A little bit of physiology, but this is where we're going to cover it. So I'll see you in the next video to learn about ossification, as well as some conditions of bone.